yeah, without further ado, yeah, please take it away.
Thanks, Shane. Good afternoon, everybody. Shane's introduced me superbly already, so I'll just skip straight ahead. My email will be shown at the end as well if you do need to get in touch with me. So we're now trying to start all of our talks in Trinity by actually explaining who we are before we leap into stuff. So as Shane says, this is me, Lewis Jones. My pronouns are he, him, and that's where you can find me on Twitter. As an individual, I should qualify, it may not be professional. If you want to follow my group for more professional content, right? I'm originally from North Wales, and so this is me. I think my students might be online, so they might find this amusing. And then I spent a good while in Oxford doing an M.Eng in materials science, where I did my final year of that 4 years abroad in California. You tend not to get sunsets like this in Oxford on the beach. And then I did 4 years of a PhD in electron microscopy with Professor Pete Nellist, who was good enough to let me stay on as a postdoc. 3 years funded by the European Union, and then a year funded by Jail and Johnson Matthey. So I moved to Ireland in 2017 for this newly created position in ultramicroscopy. So I'm based in the Advanced Microscopy Lab down Grand Canal direction. And I'm now, as Finn says, I'm on a 5-year Royal Society fellowship, which is great because I get the flexibility to investigate a bunch of mad stuff that probably wouldn't normally get funded. In 2019, Trinity got this joint SFI EPSRC Centre for Doctoral Training in the Advanced Characterisation of Materials. So we take an average of 5 PhDs a year through that route. We're looking for 7 in the advert that's live now for next year. So if there are any final year undergrads, take note of that. And from earlier this year, I'm now the president of the Microscopy Society of Ireland. So you can find details of that at microscopy.ie. And we have our national conference coming up next year, April 6th to 8th in Galway. Okay. This is where I'm based physically. I mean, you guys don't need this map, but this lovely, typically engineering science looking building is down in Grand Canal. We have 6,000 square feet of custom lab and office space. It's operated as a user facility, so you guys would all be eligible for the SFI approved access charge rate. Instrumentation is all described there, and you can follow the lab and get in contact with that email. And that email goes to all of the support staff, so the most relevant person would come back to you about your question. So Shane asked me to include a couple of slides of undergraduate physics because he tells me that some people are undergraduates in the call. So this is actually the building where I do my lecturing on the Trinity campus in physics. So it's only 3 slides. It's not going to be a physics undergrad lecture, right? So I just wanted to recap Rutherford scattering. So this is a phenomenon that was observed over 100 years ago. Fire a bunch of alpha particles towards a gold foil. Most will go through and nothing happens. Some will be deflected by a large angle. Even smaller numbers, this is a log scale, will be deflected by a significant angle. So that really just told physicists that the nucleus was small compared to the bulk of the material. Alpha particles normally require a radiation source, the exception being a helium ion microscope, which you can ask me about later if you're really interested. But electron beams are generally easier and safer to create. Some of us are old enough to remember the old CRT televisions, and they all had an electron gun in the back of a television, right? So they're not that difficult to build. Electron scattering is easier to deal with, though, for us. So we take our back of a TV type gun, and now instead of, whereas here, the positive alpha was deflected by a positive nucleus, in the same way, an attractive force can create a similar high angle deflection. So that's what we're doing. This tap represents our electron beam, and this sample plastic rod might represent our nucleus. And we're interested in my work mostly in this high angle scattering. All right, that's the first slide. The second slide that we'll be using later is this photoelectric effect. So, this is great. I've really always wanted to build one of these for my lab, but I can't. All you need is a vacuum chamber, some sort of potential difference, some light, and then some sort of crystal. And if you strike this material, doesn't have to be a metal, usually though, with a photon, if you give it enough energy, it'll be liberated from the metal and can then travel towards the anode here. All you need to do that is a light source with a greater energy than the work function. We can optimize, we can increase the energy of these electrons either by increasing the energy of the light or choosing something with a very low work function. And what I love about this, if you rotate that undergraduate setup, that looks straight away like an electron microscope with an emitter at the top and a beam going vertically. So yeah, happy days, right? So we're onto something there. The last of my 3 slides on this refresher stuff is left-hand rule and electron lenses, right? So this is always fun to me. A solenoid, if we was in an electrical engineering, we'd be talking about relays and things that open door latches. But all it is a coil of wire generating a magnetic field. And you can make the field stronger with more turns, more amps, or make the gap smaller and the field will be denser in this gap in the middle. Now, this probably won't work for the people joining remotely, but you have to trust me, you can take your left hand. And if we look just at the top part of the lens here, right, the electrons are traveling down, so conventional current is traveling up. Let's just look at this last little field line in blue here going from left to right on the slides. I'm trying to get this right now. Field is going from left to right. The conventional current is going up. And so the force on an electron just clipping that right is into the screen. Okay. Now the component of the vector of that's motion is into the screen. Look at the field lines here going up. Okay, with that motion into the screen, the current still going up and that force. Now the force is towards the central axis. So as soon as the electron enters the lens, it starts to spiral. Once it's spiraling, there's a component of force towards the center. Okay, so all electron lenses are convergent, focusing on electrons. Okay, so we can produce electrons, we can extract them with photoelectric effect, we can focus them right, slap it all together, and you have an electron microscope. I'm mostly interested in my work about ADF STEM, so this is angular dark field STEM. And using that focusing effect, we can make a beam quite routinely less than 80 picometers in diameter. Okay, so much less than the distance between atomic columns in a projection of a crystal. We can scan that beam, so that's this S in STEM. We scan that beam across and collect the data pixel by pixel, plotting out the magnitude of this Rutherford scattering as collected on this large donut-shaped detector. Okay, so for every pixel position, we just store the intensity that gets scattered to that ring. And we get an image like this. This is an experimental image. This is an image of silicon in a 110 projection. And if you take this centimeters, it's 10 to the minus 2 into 10 to the minus 9 here, this is about 10 million times magnification of a crystal of silicon into a real image of silicon. And I think it's very pleasing. All right. What's it useful for, though? So the reason we love that Rutherford scattering, that incoherent imaging mode so much, is it's relatively easy to interpret. If you have more mass, if you have a greater atomic number, you get more scattering. If you have a greater thickness, you get more scattering. Okay, so if you know your thickness, the brightness in these images can be interpreted as composition. If you know your composition, for example, these are reconstructions from data of pure platinum, you can measure your thickness. And you can actually count the number of atoms in projection in an image if it's well calibrated enough. You can do that in single shot images. So this is an example of reconstructions from colleagues of mine in Antwerp. Effectively, it's a time series of these, it's a nanoparticle, the same nanoparticle exposed to alternating, reducing and oxidizing gases. So you have this atomic resolution laterally, and from the calibration, you have the sensitivity to do atom counting in 3D. So that's all great. You poke 5 million euros at one of the microscope vendors and you assume you can get on with this work. Except there's a problem that was given away in my abstract, right? So I call this the Kevin McCloud theory. So if you're fans of grand designs, currently on channel 4, okay, you can't always get what you want. You can't get all of what you want, right? So if you're building a house, right, you can either have it fast, you can have it nice, or you can have it cheap. You can always get one of these 3 things. With a lot of effort, you might get 2 of these 3 things. It is impossible to get all 3 of these things, okay? I defy you to try and find an example where you can get all 3 of these things in a custom house or microscope, right? Okay, so obviously I'm not trying to do this from scratch, right? Why does Kevin McCloud? So this is perhaps better represented in microscopy infrastructure trilemma. You can't always get all of what you want. Cost is a factor, right? I mean, all of the people in this room are paying me taxes so I can do my research. Much appreciated. So value for money is important in scientific instrumentation. We want something that's high performance, right? That's how we get grants, isn't it? We have the best machine, we have the most visitors, people come from all around to use this equipment. But we also want it to be able to do a wide range of things. So it should be, multifunctional, lots of accessories, extra cameras and spectrometers and things hanging off it. Then you hang extra detectors off, you tend to reduce the performance of something else. And ideally, you'd like it to have a lot of longevity. I mean, sustainability is not just about tons of carbon, right? It's also about how long you can use something for, how many redundant duplications of specialized equipment take up room space, right? So if you do have something that's super high performance, it'll probably be obsolete in a very short order, and so you've failed on that axis. So it's very difficult to get all 3 of these things. Now, I'm not going to refer to any microscope by name, because that would get me in trouble with someone from some sort of manufacturer, right? So just think about some electronics, right? My solar-powered calculator, it is very sustainable. I will probably use that in 40 years, and the same solar-powered calculator will still be doing the same thing. But it's not very flexible. It does one thing very well. A gaming computer, yeah, great. It'll be obsolete probably by the end of this talk, right? So with an iPhone. But that would do a little bit of a bunch of jobs. You could do your calculations and your games to some extent. So it's very difficult. You can apply this to cars. You've got your Porsche, your minivan, and your diesel banger from the Czech Republic, right? Okay, you can think of nearly any field, and this holds true, okay? So in my research group, in the Ultramicroscopy group, we explore small modular technologies, normally retrofitted to existing systems. It's cost effective, in either software or hardware, to do something with one of these axes. So either expanding the performance, the functionality, or the sustainability of scanning or transmission electron microscopes, okay? So everything we do can be framed around these axes. So that's great. We have a group mission statement, but where do we get our ideas, right? So we get our ideas by comparing our idea of a microscope with the unfortunate reality. So a microscope, to a simulation microscopist, right? Electrons appear from somewhere with a perfect wavefront. We truncate them through a circular aperture. That's a perfect circle. The lens is just a Fourier transform with no defects. There's some sort of scattering and then perfect transference out to that ring-shaped detector. That is all you need to simulate those atomic resolution images. The real instrument is a bit more complex, okay? That's guns, anodes, coils, apertures that are not perfect, lenses that are not perfect, right? And every one of these things, which is different between a simulation and the real deal, is a crack where we can try and innovate in the research group. Now, don't take away from this that simulations are rubbish. It's not the case. They're very useful for planning and interpreting experiments, but the difference is where we have space to operate, to develop, okay? So we'll talk about some of these differences, right? So we should have a perfect, this is an example, a lovely figure from Christian Dreyer. A perfect emitter and a perfect lens would give a perfect dot of illumination on the specimen. We don't have perfect lenses. They have defects and they're truncated in numerical aperture, so we get something like one of these Bessel functions. And even if we did have perfect optics, the electron emitter has a finite size that you can only demagnify to a certain extent. The sample looking up to the emitter, the microscope is a demagnifier, right? And so you combine an imperfect emitter with an imperfect lens and you get some combination of all these effects. So, we can now incorporate these into simulation. The simulation packages are maturing, getting better. And there's a recent reference there to a second iteration of this. And this prismatic 2.0, unlike 1.0, can now include something called chromatic aberration, that finite source size, and even just the stochastic noise from using a finite beam current of electrons. Now, I see in the room, everyone is male, right? For this next experiment, that's useful because men suffer worse from chromostereopsis, right? I practiced many times saying that, right? Now, if this has worked, I don't know, you might see it better on the dark monitor, I'm not sure. The red lettering should appear to float above the blue background. I will try. Does that help if I do that? Can you see it better? So you will struggle to focus on the red and blue at the same time, okay? The blue is focused more strongly by your eyes, and so your eyes relax. Your brain thinks that the blue is further away. The red is focused less on you. You look further away, so your brain thinks that the red is floating above, okay? If you don't believe me, watch the playback on a good computer monitor and you'll see this effect, or Google it, okay? All right, that's in humans. The same is true in electron microscopes. We just call it chromatic aberration, okay? The colors here are reversed because it's easier to focus low energy, indicated here by red. It's hard to focus the blue. So that spread of energies, so this is showing the energy spread becomes a defocus spread going through one of these lenses. The spread along Z becomes a spread in XY. This disk of least confusion then determines your maximum resolution. So you say, oh, that's grand, that's grand. We can just buy a better electron emitter, and you could. And so this is a graph from one of my students. More performance goes from left to right. A narrow, more monochromatic energy spread is on the right, but cost is going up here on a logarithmic scale, give or take, right? And also these highest performing emitters are monochromated. And when you monochromate, you just throw away the bad electrons. So your actual beam current becomes, in extreme cases, vanishingly small to nothing. So the question is, well, what is the best range to operate on here? Down this end, you've got excessive chromatic aberration. Up this end, you'll have excessive shot noise because you've no functional beam current, okay? And just for completeness, if you take away the saturation of that, they will now come into the same apparent depth to you, all right? So this is explicitly investigated. My students have simulated here for 4 different badnesses of lens. So these are 4 different chromatic coefficient lenses, an impossible perfect lens at the top, and 3 real lenses that you can buy on the market now, and a range of energy spreads from right to left. You're losing beam current. I don't know if this comes out well on the projector, but for this top row, more beam current is always better if you have a perfect lens. It's an obvious no-brainer, lovely signal to noise, and these images get more noisy. But down here, this image gets unacceptably blurry in that case. And so there's a trade-off in the middle ground, and that's easier to see on these graphs that are enumerated, okay? And so depending on your prescription of your electron lens, you want to be somewhere around here in the 100 to 200 milli-electron volt range to get the peak of this signal to noise. And you can, if you had a monochromator, you could tune that to get the very best possible performance from your lens. That's grand, but that's $500,000. I don't have $500,000. We'll be passing a tin at the end. Okay, so this is a problem. But in that slide I showed you earlier, we might have an option here, right? I said the photoelectric effect, you need an anode and you need a vacuum chamber. And that's what we have in the gun region of an electron microscope. This is now, this pink crystal is a lanthanum hexaboride crystal, has a low work function, and off-the-shelf UV lasers have an energy greater than that work function. Okay, so this is actually what one of my students has done. We've retrofitted these lasers into here an old SEM that, you know, won't be missed if it exploded. Bit of 3D printing, off-the-shelf lasers, and she's now got this UV system. We think some promising preliminary data, about 100 picoamps of beam current. That's hugely exciting because the laser is intrinsically monochromatic. The work function is intrinsically singularly valued, okay? And so we think this is going to produce an emission of around 110 milli-electron volts. That's about 3 times better than what's considered a good cold field emitter off the shelf. Okay, so that's why we had the photoelectric slide. Now, again, I picked this manufacturer just because I had to have an example, but this is an issue of all of the main manufacturers. Different microscopes are optimized for different tasks. This one might be optimized for ultimate resolution of solid state materials. We might want something for catalytic development that has a mixture of resolution and chemical analytical capability. And in the life sciences, you know, they're not going to such magnifications. They can back that off a bit. They might prefer to have more chamber size and specimen tilt. Okay, but there's actually a massive amount of duplication because the only real difference between these 3 microscopes is that little yellow bit in the middle there, the gap in the pole piece of the main objective lens. And each of these will have cameras underneath, spectrometers on the side. They'd be typically €1 million each, up to €1 million, I should say. And so, you know, a world-class facility will have 3 of these rooms side by side and 8 hours of usage in the 24-hour clock on each machine. Okay, if SFI's in the room, don't wince at this. You know, it's not my fault. That's what this looks like inside: a small gap, a medium gap, and a large gap. There's a few other small differences, but that is the main difference from a hardware point of view. Okay, and there are no other areas of science I know that accept this hand tied behind the back type restriction. Okay. Hundreds of years ago, we got over this problem in light microscopes. So this is an example of a light microscope with a multi-objective setup. There's probably dozens in this very building. In the electron microscope, we just have that one fixed lens that I showed you there. And you know, like I said, a material scientist or a life scientist probably wants something different. Flagship machine these days, you're talking about $5 million, €5 million, depending on the options you have equipped. And you'd probably hope that you'd get 10 to 15 years. Probably out of that, you get 2 or 3 years of bragging rights before it's obsolete. See previous slides, but you'd keep it running as a training instrument maybe for 15 years. Okay. What should go in this space? Well, the answer is a pole piece with an adjustable gap. And so that brings me to the second project that the group is working on. Okay, so here you can see a mechanically operated moving pole piece that will be retrofitted effectively to that giant solenoid, the objective lens. And if this works, it'll enable material scientists to use the machine in the morning, a chemist to use the machine in the afternoon, a life scientist to automate something overnight in one instrument. And for a country the size of Ireland, that's a very good economic proposition to not spend the second and third wave of 5 million. Okay, the gaps we're designing for cover the range of 1.5 millimeters to 5 millimeters, and that's smaller than the small gaps now and bigger than the big gaps in the range. And the moment we're designing it for the JL microscopes with the primary beam of 200 to 300 kilovolts. This requires a lot of calculations to get it right. You know, the manufacturers have a 75-year head start on designing these lenses, so we're coming as outsiders to this. But this is COMSOL modeling of that solenoid. The coil's in gray there, the field intensity shown in the color spectrum here. And these plots show the magnetic field down the z-axis of those 5 lens gaps in the middle. A perfect lens would be a nice delta function that would have 0 aberrations. And you see here, going from a better lens to a worse lens in that trade-off between tilting range and spectrometer space versus resolution performance. We can also use these simulations to design, to predict, I should say, the saturation points. Maybe we can change the geometry before we machine them. That's then what we do, because it's all well and good to simulate stuff, but at a certain point you actually have to start building. So this is from the physics workshop in the city center. And then this one is stepper motors and brass gears making the whole thing move mechanically in a test bench in my lab. This sub-project is a sort of a makerspace inside the group. There's more details there, a separate Twitter just for this project, and we will be looking for new staff and PhDs in this area actually fairly soon. Okay. So that's okay. So look, we can make a new emitter, we can make a new electron lens. We still have this fundamental limitation that the scanned TEM is a scanning microscope. And if anyone's done STM or AFM or these sorts of things, you well know what can happen. So this is an example of a atomic resolution image of bismuth ferrite. It's going quite well. My colleagues saw that and thought, oh, come in and have a look. They shuffle in carefully. The pressure wave from opening the door pushed the sample, half a nanometer. I don't know, it's a very small amount, but big on an image that 20 million mag. They shuffle in nervously. I sit down. I'm going to watch this. Oh God, I've left the door open. Temperature drift will affect the instrument. I go and close the door. So then they ruin the image twice, closing the door, and the scan finally finishes. Right? So a crystallographer would look at that and say, well, the angles are not 90 degrees. The unit cell length is not square. To a crystallographer, this is filth. Okay. A few seconds later, this image was taken. The only difference between the image on the left and the image on the right, the image on the left, each pixel was 40 microseconds, recorded as a single scan. Takes about 10 seconds in total. The image on the right, every pixel was 2 microseconds, but we took a burst of 20 images. There's then 20 redundant observations of the same underlying structure. It's fed into software that looks for the differences, inverts them with non-rigid registration, a technology from the medical world. And now you get perfect right angles, perfect unit cells, and a vastly high precision image. The same recording time, the same beam current, the same total electron dose, right, 20 times more hard drive, but that's cheap, right, compared with the instrument time. Okay, so this multi-frame non-rigid registration is nearly our default working practice across the STM, AFM, and now the TEM. The different kind of problems that can come into your data purely correlate with frequency. So scan noise was a big part of my research in sort of 2013. Turns out you can solve that with thick curtains because it's in the audible frequency range that disturbs the data, right? Bungee cords are used on STMs a lot as well. Line sync that the manufacturers have dealt with fairly well with better power supplies. But this blue and green here, the image drift and scan distortion, these are really insidious things that are very difficult to correct, okay? What they look like is, this is an example from STM, and a fine transformation with this very slow drift, or this mid-frequency, this is what we tend to see, a non-linear, a time-varying distortion during the image scan, okay? This fine effect here has been known for a long time. If you're scanning from top to bottom and then bottom to top, the matrix defining the affine transformation is equal and opposite. So if you record 2 of these images, that's enough to have a redundant set. That was sort of reinvented in the electron world. Some work here. You can take any 2 opposite images here, and the affine transformations will cancel out. So what we often do now is we record with the scan rotation program at 0, 90, 180 to 70, 0, 90, 180 to 70, and that just encodes even more redundancy into that 20-frame burst series. It's a very useful approach. Has some problems we'll see later though. So that was all written up around 2015. This smart line algorithm will accept nearly any kind of image series: time, focus, rotation, camera length, correcting for translation, affine, and non-linear. So that's this non-monotonic thing. Importantly, no assumptions need to be made about periodicity. So if you're looking for periodic structures, or you're worried about artifacts in your data, it's impossible to introduce those. I say it's compatible across other types of microscopy. I've even used it on astrophotography data, taking out the atmospheric oil from telescope videos. It's a bit of fun. We also have a software that can also take control of the microscope, so you're not endlessly clicking and saving hundreds of images, which was a problem in the first version. Right, and then so this has been heavily used in the community the last 5 or 6 years. Routinely now, people getting to precisions of 1 picometer. Now, importantly, that's not resolution of 1 picometer. I mean, that's beyond the wavelength. It's not going to happen, right? But resolution is what you can see. Precision is what you can believe. So that's the reproducibility in the data. Say adjacent unit cells in a perfect single crystal of silicon. The reproducibility is within 1 picometer, and that's been well studied by many groups, independent from my own research, to fact check what I say is true. Okay. I just throw out one pretty picture because it's nice to be nice. This is a large field of view image of the strain field around a magnesium-rich precipitate in 100 aluminium, and this colorization is the shear strain. Okay, so if there is engineering people worried about that, the strain hardening of alloys, we can see the shear strain billowing out of these without the normal scanning wobble that you would see in STEM data of the same thing. So that's great. That's great for images. But one of the reasons why this scanned probe is useful is every time we put an electron beam on the sample, we get X-rays, we get energy loss spectrum. Every point gives us rich information. So if you take a spectrum at every point, you get a 3D data cube. If you put a camera in the diffraction plane of your microscope, you get 4-dimensional data. And 4-dimensional data, we can reprocess that to get that into a pixel series, and then it's back to 3D. Has the same dimensionality as a spectral volume. And in the spectral volume, every, say, energy slice has the same probe distortions as the image slice, let's call it. So whenever we get the diagnostic from the image series, we can just run that through the volume data series and correct all the spectral volumes and average them and add them together without losing resolution that you would get if you added the data together without removing the wobble. So this is data from the neon microscope that sits in that handsome brick building I showed you earlier. There's an enclosure inside of a room. The microscope is then inside all that box. And so just what we're plotting here is the image, which is just that Rutherford scattering in black and white. The X-ray here, the bismuth is in green. Those 4 dots there correspond to the 4 really bright bismuth from the Rutherford scattering. And then the iron and titanium, you can see those are the lighter gray dots there. What I love about this is those 5 dots of the titanium and the iron, they're coincident with one another. You see that the last row of the iron is denuded and enhanced in the titanium, so you get that 2 different shades of purple there. So you actually see the local stoichiometry at the atomic scale when you have the right specimen and technician operating the machine. From the sort of 4D camera work you can do, there's a lot of interest these days in 4D electron microscopy, and tychography is one of the leading topics there, because you can get phase images from the same information, and phase imaging is much more sensitive to light structures. So this is a single image of monolayer graphene. Graphene is a great test specimen for me. I mean, I'm not so interested in the resolution. You turn the mag up, you'll still get hexagons, right? But why it's interesting for me is every one of those carbon atoms should be identical. The phase plot of that should be identical. And so in this image on the left, which has these small scanning distortions, the integrated phase of each column is plotted out here in orange. After distortion correction of that data set, the phase precision is better. So, I mean, I'm not actually studying graphene, but if someone was interested in 2 nearby things, or the difference between lithium and boron, or whatever it is, phase precision is what matters. And again, like I said before, resolution is what you can see. We can see it's graphene. Precision is what you can believe, right? This is a bit of a deep dive into these angular detectors. I just showed a perfect ring earlier. That is not true. Scintillators are never that great. And to be honest, these are Geiger counters with bells on. The technology hasn't really moved forwards in the last 50 years, okay? And so, this detector from company 2 here, letter D, the color scale here represents the efficiency of the scintillator photomultiplier combination. An electron hitting here will give 3 times the signal as an electron hitting here. That's very rarely incorporated into simulation packages, right? So this really matters that we get a homogeneous response from the detectors, okay? We'll see why that matters presently. But first, we need to talk about the radiation dose in our microscope. Okay, as a general rule, you should try and use the minimum amount of radiation to achieve any given task. This radiographer here, smiling, she's the one with the lead apron. She's happy. The child without the lead apron, not so much. Okay, so always remember, use the minimum dose you can to achieve a task. The dose, I really should say affluence, I think is more accurate in our microscope. We just need to know the beam current, the Coulomb number, that's just conversion, the time we spend in each pixel, the area of each pixel to normalize, and if you're doing some scanning trickery like compressed sensing, there might be a fraction less than 1 of the pixels which you choose to illuminate. And you pump this in, you get doses, for material scientists, this might be 10 to the 8 electrons per square angstrom. For a biologist, they'd want to be 6 or 7 orders lower than that to avoid frying their material. And you could do things like compressed sensing, but they need very expensive scan generators, acquisition systems, and things like that. You can turn down the magnification, but I mean, that kind of defeats the point of having the resolution. So the two things you really have free control over is reducing the beam current or scanning more quickly. Okay, just faster video frame rate stuff. And the good news is these photomultipliers are sensitive enough to single events. I mean, like I said, they were developed from Geiger counters. They are originally counting tools, right? So they are sensitive enough to see individual electron impact events and produce a pulse in the signal. But you have to run the microscope at an incredibly low beam current to give enough time between each individual impact event. Okay, that's okay. And different groups have reported similar shapes. If you connect up a really high-speed digitizer, you can see that all the ones in the literature are all actually correct. You just need a much faster capture system than is available on any instrument today. Okay, so you think, oh, that's great. We can use one of these fast, high-speed streaming oscilloscopes to look inside what would normally be a 20 microsecond pixel, and then that would just be the whole of the next pixel. I think, oh, that's great. We can count the electrons as they come in. But let's say if you put a threshold here at 50 millivolts on the PMT, you'll miss that pulse. You'll think that one's 2 pulses, and so on and so on and so on. The afterglow streaking from the scintillator PMT combo is too slow. But now this is work led by the postdoc and another student, where they realized the gradient of that signal is actually very sharp and easy to count. You just count on the leading edges. Okay, so we started off forcibly taking the gradient, and then you have a much easier digitization process. Even these 4 pulses here piled up are actually separable, which I think is a lovely piece of work from that group of people. We were doing that by brute force at first, and then more recently in bespoke circuitry that the postdoc has designed, and the PhD student is now operating this on the microscope. There's the original incoming signal, all different heights of the signal there. After digitization, every electron is recorded equally. So that speaks to the quantum efficiency that every electron is treated fairly. There's no strong and weak parts of the scintillator surface anymore. And then we turn this intensity, becomes more like an actual scattering rate. So it's a full particle accelerating interpretation. There's a weak rate of scattering in the carbon support and a rapid rate of scattering when the electron beam goes over a gold nucleus. And that's a very, very pleasing statistical approach. And that team got the cover of Microscopy and Analysis earlier this year. When you look at that sensitivity scan that I showed earlier, that's that subpar detector on the left, let me say. It's the same detector. On the right is the digital counted analysis of the exact same simultaneous data. And we now have an electron counting sensor with perfect efficiency without having to break the vacuum and change the hardware. So this is like getting a new detector just by retrofitting new electronics. So that's quite pleasing. It's quite sustainable. And there you go. So 2 different pulses now become the same height. Okay, so that's addressed the issue of going weak in beam current and getting every electron recorded. The other thing is, just scan faster. And that's fine. You have in your head that a perfect raster scan would look something like this, except it's not true. These scans are done by coils, deflecting the beam, still like the old televisions. And there's an inductance at the start of each line that means half of the frame is not usable. So the way we normally get around this in the community is we hide the flyback waiting time at the start of every scan line. That's okay. If that's a scan that's 1/50th of a second and you lose 100 microseconds, you don't even notice. But if you go to faster and faster video rates, that overhead becomes crippling. to the point where 90% of your beam is just causing damage and not yielding any actual data. So that's kind of disappointing. And what you can see at the microscope, you just turn this knob faster and faster. The start of the frames get more and more compressed to the point where you get a sort of a nearly 20% contraction in the unit cells. And the crystal didn't shrink. We use these perfect crystals, in this case, strontium titanate, as a nano ruler. Okay, so that's purely a 20% artifact in our imaging system. However, it's the same artifact every single time. Every day, it's the same. So we can calibrate this from very boring crystals like silicon, strontium titanate, save this data to disk. We know how to correct that. This is the exact same data shown after correction. The reason we discovered this is because, like I said, there's great reasons for processing the scanning orientation until you discover that all 4 edges of your average image are corrupted, and there's only a little bit of field of view in the middle that's workable. You take the same data set and pre-process to correct for that flyback hysteresis, and this is the exact same data set is perfect out to all the 4 corners, maintaining the frame rate, maintaining the redundancy from the scan procession, and the multi-frame non-rigid registration. Okay, so that's us. That's the group. That's our couple of interns there. So I think we peaked at 10 people over the summer. Yeah, I said we exploit small, modular, retrofitted stuff. Sometimes we make our own PCBs. Sometimes we use our 3D printer to make brackets and stuff in software and hardware to expand performance, functionality, or sustainability of these microscopes. I didn't show you the stuff we're doing in the scanning microscope because we've gone over time. But you can look at these different things I show here. You know, this is just the recap. You know, the multiple focal length objective lens will expand the functionality. We have things like the non-rigid software and the electron counting, increasing the performance without having to replace the sensor head. And then we have things coming along like the UV photo gun and software compensation of the hardware hysteresis, expanding the longevity because we don't have to change the coils or the gun whilst adding another performance, say here with a more monochromatic beam. Shameless plug, we are looking for people to join the team soon, including a project manager at the IUA senior fellow scale, a postdoc, and another PhD to work on the electron lens project from next September, which is fully funded. You can see all of that at the group website or follow the group Twitter. And I'll finish and leave time for questions just by throwing up the funders and acknowledgements for some of the people that gave me samples and collected data and things like that. Thank you.
Okay, so maybe we'll ask to see if there's questions in the room first.
For more simulation or more.
Yeah, so the question for people on the Zoom was, where will simulation and experiment converge sort of on the sliding scale of perfection, right? So it's a good question. So in the sort of 70s and 80s, people put a lot of effort into understanding why electron cameras were poor and adding that into the simulation. But the thing is, that's a kind of a pretty fudgy knob you can dial in to match nearly any experiment to any simulation, right? Our preferred route is to work the other direction. Take, for example, those electrons that were sometimes 3 times more efficiently collected than others. Well, if you go digital, then you bring the experiment closer to the perfection of the simulation. And I feel like that's more reproducible than me having a fudge factor for my camera or the afterglow streak or whatever it is, you know? So I would prefer to see people bring the instrumentation higher in standard. Now, that being said, because we've spent so long studying these phenomena, we now know how to make a simulation look indistinguishable from real data. And that has interesting consequences.
I was wondering about, is there any use for like deconvolution techniques?
Yeah. There is a little bit. I find people in the community are nervous of deconvolution. There was once in the late 80s high entropy deconvolution. The problem with that was the image you would get out of the software depended on the pixel size, which physically is alarming, right? And I think deconvolution's had a bad name since then. But I think what people are more inclined to do these days is, for example, fit a Gaussian to 2 atoms and measure the difference between the distance between the fitted Gaussians. You know, because that's directly working on the data. I mean, you could deconvolve them to see 2 dots. You'd measure the same distance, right? So I would probably, we don't get involved in deconvolution. You know, I'd rather fit to the data and understand the fit than.
Yeah, I was just wondering if you showed the variable separation device that if the instrument response, was quite crazy at one of the edges, that maybe it would help.
So one of the things that's pleasing with things like the multi-frame averaging technique is we reach the performance of the optics. Previously, we were limited by the performance of the scan or the room stability. With that technique, we reach the performance of the optics. So then when we're at that performance, the rest is witchcraft. I don't normally go into the deconvolution. I just do. If we get to the absolute performance of the lens, that'll do.
Are there questions online, if you can hear me? Because there's so many people online, I was wondering, give you the opportunity to ask questions as well. I think if you unmute, we can actually hear you, but
I'll wait for that. You emphasized the distinction between precision and resolution in this. And it's interesting to me because I'm wondering what's typically the distinction, or not the distinction, what's typically the difference between the two of yourselves? Do you have resolution finer than the precision? So you essentially have something akin to the limited resolution, like looking at a telescope in the atmosphere, or the precision will typically be lower than the
So for those on the Zoom, the question was, I think, what is the difference between precision and resolution, and when does one exceed the other, and when can that happen, right? So it's a good question. You can get situations where either exceeds the other. So let me give you an example of an image of a single crystal of silicon, where all of the atoms are visible. You've resolved that dumbbell distance. I should know what it is, but I forget, right? But overall, the image is wobbly. So that has high resolution, low precision, okay? The other way can be two atoms which are barely resolved with a very weak dip between them. That has very poor resolution. But if the scanning is perfect and the signal to noise is vast, it might still have high precision, which is the reproducibility of a measurement. Okay, so it can happen both ways. And I hope that each student that leaves the groups should know by 4 years where to spot which is going wrong, because that's where you invest the effort, whether you need effort in optics or effort in heavy curtains, right? One is cheaper than the other. So, it's important to spot which one is the problem.
okay, very good. Any other questions from the room?
Before, some things are not in lithography. So what if any of the techniques have applications where you're deliberately using a similar setup principle to etch?
Yeah. So the question for the Zoom was, are any of these hardware innovations useful for, say, e-beam lithography? So I assume so. I don't work in EBL myself. I don't know of any systems that are, for example, monochromated. And actually, they don't require very much beam current. So things like the photoelectric emitter might be useful, not sure. I think things like the adjustable focal length objective lens might be useful in something like an Auger system, where you want to have a trade-off between resolution and maybe getting another detector in to look at light emission. I don't know, but I hope more that people really take away the ethos that, don't be afraid to modify the equipment. Like, so if we go horribly wrong, I can just remove that circuit board and put everything back how it was. Right? As long as we don't squirt high voltage up the wrong line, it can be removed just as easy as we retrofitted it. People are very concerned about voiding warranties, but if you take away the ethos of just have a go, we'll get back to where experimental physics was in the 70s. But think the instruments are so expensive and the insurance contracts are so expensive, most people don't try. So yeah, if someone in EBL wants to give it a go, you can get in touch.
Was there any other questions? No.
And again, do please get in touch by email or on the website or the Twitter if you're interested in these two postdocs or the PhD for the next calendar year.
Okay, well, we'll thank Lewis again for a great talk.
Thanks, Shane.